Hello everyone, I'm very honored to be here, and today I'm going to present about why standardization allows the law of scale in terms of physical AI. So before we dive in deeper into today's presentation, let me briefly introduce about myself. I am currently working as a managing director of self-driving and robotics division in Maum.AI. So let's go back to the presentation. So we truly believe that the next GPT moment is coming, and it'll be forms of a physical AI. Many analysts, such as Morgan Stanley, has predicted that robotics and physical AI will likely have revenue impact much more earlier than expected. And as the physical AI's domain is more about replacing human labor, this market is valued at tens of trillions of dollars. So even a small slice of the market can generate high profits. So what is physical AI? We believe that the physical AI is a new paradigm where AI systems have physical embodiment, interact with the real world, and perform physical human labor. So in 3 short words, it is space-aware, it is real-time adaptive, environmentally coupled, an AI system built for a physical world. So, physical AI, the terminology is so vague. What is it? What is under the hood of physical AI? We believe that vision language action models, VLA model architecture, is the core of physical AI. So, what is vision language action model? It can understand, it can plan and execute just like humans. So let me give a little bit more detailed explanation. It has a human-like scene understanding from cameras. It has a large language model at the center, which has common sense and logical reasoning, understanding, and acts on natural language instructions. And last but not least, it executes precise navigation and tool manipulation control from its reasoning results. So let's talk more about why language actually matters. Many of you, or many of the conventional robotics engineers can say, why do we even need a language in terms of model capabilities? Vision action models, such as reinforcement learning, already works well enough. So I like to give a very simple analogy about doing some kind of task. Say that I want to move this kind of object from point A to point B. It is a fairly simple task to be done. And say that we're training an insect to move this object from point A to B. How long will it take? I believe that we'll need astronomical amounts of time and effort put into insects to move this object. But let's put it up a notch. What if that we are training a dog to the same task? It'll take about hundreds of hours, but we can make a dog to do the same task. Then let's think about humans. If I ask any of you to move this object from point A to B, I mostly think that most of you can do in a moment of seconds, because we are able to understand the intention and the task via language, logical thinking and languages. So VLA approach, performing common sense reasoning and decision making throughout language, definitely reduces the astronomical amounts of data and compute needed for doing the same task.
We compare Canvas with RAW's
Let's
NavStack,
show you
a straightforward
how a vision
yet
language action
effective
model might
rule-based
work in
navigation
real-world
system.
scenarios.
In the
red
sidewalk
trajectory,
scenario,
is
both
the
systems have to
trajectory
involve
that was
correctly
given
crossing
for
roads
the
and
robot to
staying on
drive.
the sidewalk.
So,
Canvas
typical
consistently
expert
adheres
systems
to the instructions,
very
especially
faithfully
when
follows
faced
the
with
trajectory
misleading
given.
information, by learning common-sense
Then,
driving rules from
you can see
demonstrations,
something,
unlike NavStack,
exciting.
which relies
We
on
given our VLA model a language instruction. What have you given? We've given the task that you must use the crosswalk in order to drive. So let me turn the video again. the AI model actually doesn't follow the given red trajectory and makes a decision. Oh, I need to use the crosswalk. And the model follows the crosswalk. So actually, it had understood the concept of a crosswalk and put it into a real-world actions. So many of you might ask, are Maum.AI the only ones that are truly believing the future of vision language action models? But I can clearly say that this is a global phenomenon. There is a clear global shift to vision language action models. Frontier researchers such as Tesla, Figure AI, Baidu, AGI Bot, they're all using VLA-based end-to-end adaptations in their frontier researches. So, I have explained about physical AI. I have explained what is under physical AI, the VLA architecture. And now, let me a little bit talk more about how physical AI differs from legacy automation. So this is a very shortened explanation, but typically, rule-based expert systems are like thousands of codes, thousands of lines of hard-coded if-else rules. But physical AI, it is more like data learned, data-centric policies learned and using VLA to drive planning. So what is the critical differences between those two? There are many pros and cons between each technologies, but I believe that VLA could scale exponentially with more data and compute if we found a good scaling law to scale our VLA models, just like large language models. But clearly, expert systems have a very clear ceiling. Progress scales very linearly with engineering input. So these are the domains that physical AI might be utilized. Maum.AI, we are currently commercializing extensively on brownfield industries such as agriculture, defense, construction, mining, manufacturing, and so on. And last but not least, in order to succeed in physical AI era, we believe building the data is building the lead. Because as the technology progresses, new AI model came out, new architecture ideas came out in the field or in academia. But the data, especially if the data is very domain specific and industry aligned, that will be any company's exclusive defensible mode and asset across the physical AI industry. Then let's briefly talk about Maum.AI's our experiences, and then let's talk about standardization. So Team Verve, the team that I'm leading, have done a few things, but I want to tell about two things in today's presentation. We were able to pass the National Autonomous Agriculture Machinery Certification. It was the first using physical AI, using VLA systems to pass all of the government regulatory systems. So we are commercializing our products B2C in South Korea and Japan during this year and next year. Secondly, we are writing a lot of research papers to contribute to physical AI ecosystem. Many industries, many companies don't release their researches because they think their technology is very noble and advanced. But we're spotting on the very different way. Physical AI system or the ecosystem is very, very new. And we need a lot of interest and communities and the academia to join in to proceed. So let's move forward. Physical AI has a very sophisticated and interconnected value chain. If you use any robotics or physical AI, we might need compute, sensor, actuation, power. And if you use AI, we need VLA systems, simulators to test our AI models before deploying. We need teleoperation to collect data. And we also need a sufficient GPU or network in order to achieve the compute task. So in all of this domain, there is no sufficient standardization, which is a very critical issue in order to find a physical AI scaling law. But from all of this domain, today I want to talk centrically about data standardization. Why data standardization is essential for scale? So in LLM, large language models, because that we have standardized using Unicode UTF-8 for subword tokenization, we were able to we are able to make a reproducible scaling law and in a compute optimal training way. But vision language action models still lacks very comparable data time action intermediate features. With only pieces like MCAP, like Google have suggested, and PTP, that kind of system were being known. So we need a lot of things to standardize in data. So let's go into a little bit more details. The current issues with physical AI data standardization. There are many formats, but majorly I want to talk about two things. Currently, physical AI data is very weak on large-scale video and media support. Secondly, because many of the companies are trying to use a single format pipeline, it cannot effectively be optimized on both data recording and model training pipeline. So in terms of Google, RLDS pipeline platform, the data formats, it is originally defined to use for reinforcement learning tasks, which is very vulnerable for large-scale media video processing. If you use this kind of formats, we really need a lot of data. We need very large storage in order to do any kind of video-based model training. Secondly, many of the researchers are using Lee robot data set or that kind of data architecture. Companies like 1X, Scale.ai, they're using that kind of data format to do their research. But what is their problems? They try to use a single format to optimize both features, like data collection and model training. But this is systematically impossible to do because they require very different optimization strategy. So if we try to use Lee robot data set, it is very bad on distributed computing a storage platform especially because they have very small data parts all across the field. So we need to do optimization on that front as well. So what we have found out and what we try to do is we try to open source our findings in a very ecosystem-friendly way. Here comes our project, Open World Agents. We try to solve a few problems. First, dataset compression issues. Second is optimized training efficiency by two ways. First of all, we try to separate the video storage by media ref and separate the sensory data and the video data apart and reference it via MCAP file. Secondly, we have used optimized recording optimized MCAP format to collect the data, and before training, we transform the existing data formats into training optimized data format. So let me show you our solution to solve this kind of pipeline problems. First, we collect data in a very recording optimized way. And then before model training, we changes the existing storage efficient data formats into a training efficient data formats and store the data on AI training servers such as H100 clusters. So with this kind of strategy, we could effectively store image data, video encoding data, and then multi-rate sensory data, which means in the physical AI robots, we use various sensors, but all of the sensors give out on different frequencies. Like LiDAR, they give data points on very high frequency. And if you use some kind of other sensory data, they use different sensory frequency. And then we can also achieve discrete events and store it effectively. And not only this, in order to scale effectively in physical AI, we need to obtain large scale of pre-training data for the robotics foundation model. So we have also released a pipeline for any researchers to collect YouTube scale gaming data and change it into a manipulation or navigation helping training data sets. So you can also search it in our GitHub repository in order to use it freely as any of the researchers might want. So with this kind of methods, we have succeeded in making our 1 billion parameter model much more effective than already existing 7 billion parameter state-of-the-art AI systems. So this is our presentation, and let us come together to build a unified ecosystem for physical AI, because there are very lots for everyone to help in this very exciting domain. Thank you.